So the very first simple application of our formalism is going to be a simple model of paramagnetism. Just a few words about magnets. There are different kinds of magnets that are distinguished by the way they respond to an external magnetic field. There's the paramagnet, which if you apply an external magnetic field, then its magnetization will, well, the stronger the field, the higher the magnetization, and the magnet will align with the external magnetic field. One example is aluminum. Then there's the diamagnet, which has the property that the magnetization will have the opposite sign. It will anti-align with the external magnetic field. One example for that is silver. And then finally there's the ferromagnet, where you have the following effect. When you start with zero magnetic field and the ferromagnet is not magnetized at all, then the ferromagnet will respond sort of similar to a paramagnet. So magnetization will increase. But then afterwards, when you switch off the external field, the magnetization will not go back to zero, but the ferromagnet will retain a finite magnetization, even though the external magnetic field is now switched off. You can complete the cycle, then you can apply sort of a negative magnetic field, and then this will behave like that, and you have the shape, which I'm sure you've seen, that reflects hysteresis. So this is the ferromagnet. Now what we are going to look at now with our simple model is the first case, that is a paramagnet. There are certain substances that are have a crystal structure. They are called paramagnetic salts that exhibit the behavior of a paramagnet. And these are particularly simple to treat mathematically because the ions, which are the constituents of this crystal lattice and which carry the elementary magnetic moments that make up this paramagnet, they are fixed in space. You have this crystal lattice which is rigid, and therefore the advantage is that you need not consider any motion in space, any kinematic degrees of freedom. The only degrees of freedom are the orientations of these elementary magnets, and you need not worry about changes of position of these elementary magnets. So the basic structure looks like that you have, say here, you have an ion number 1, and there you have an ion number 2, and you have an ion number 3, and so on. And they are part of a lattice, of a crystal lattice. Each ion carries a magnetic moment. So ion number 1 might carry the magnetic moment mu1. Ion number 2 might carry the magnetic moment mu2. And ion number 3, let's say, the magnetic moment mu3. The total magnetic moment of your paramagnet is the sum of all these elementary magnetic moments. So the total magnetic moment, m, is the sum over I. I denotes, labels the ions, goes from 1 to n if you have n ions in your lattice, and you sum all the elementary magnetic moments. This is then the total magnetic moment. The N denotes the number of ions, and the mu I, that is the magnetic moment of the ith ion. Then you apply to this paramagnet, to this paramagnetic salt, you apply an external magnetic field, B. You expect that, depending on the strength of that field, more or fewer ions will align their magnetic moments with that external magnetic field. And then as a result, the total magnetic moment will be more or less aligned with the external field. Let me just spell out explicitly the assumptions that we made. First of all, that we have this crystal structure that I mentioned, which has the advantage that we can assume fixed positions of the ions. I would also like, for simplicity, to neglect any interactions between the ions. So each elementary magnetic moment is independent. Of course, in practice this is not correct. There are always interactions, but we will assume that these interactions are negligible, and therefore we can treat the ions as independent. I will also assume that the magnetic moment of the ion is due to the spin 1/2. So the electron has spin 1/2. So there's going to be, in the ion, there's going to be an electron spin 1/2, and I assume that this is the spin which is responsible for generating the magnetic moment. So the elementary magnetic moment, I assume, is due to an electron spin 1/2. This means that we can write the elementary magnetic moment of the ith ion. We can relate that to the electron spin. Now the electron spin, the operator for the electron spin is 1/2 times the Pauli operator, the Pauli matrix. So we can write this as some prefactor times Pauli matrix. So the sigma I, this is the vector of Pauli matrices with entries sigma x, sigma y, sigma z, relating to the ith ion. Now the prefactor is minus electron charge Planck's constant divided by 2m, and this is known, this prefactor is denoted by mu b and is known as the Bohr magneton. What's important to remember is that the elementary magnetic moment is proportional to, or the operator, the quantum mechanical operator for the elementary magnetic moment is proportional to the Pauli operator with the Pauli matrices, and the prefactor is minus the Bohr magneton. And finally, I assume that the external magnetic field points in the z direction. So I single out one particular direction to make it simpler. So it's a scalar b times the unit vector in the z direction. Now we are ready to write down the Hamiltonian of this simple model. And we want to focus on the magnetic part of the Hamiltonian. There might be other contributions to the Hamiltonian, but we would like to focus on the magnetic properties of the system. So we assume that the Hamiltonian has a magnetic part only. And has precisely the structure that I had shown you earlier when I motivated the conjugate of the magnetic field with respect to energy. It has the structure, the Hamiltonian is minus external magnetic field times the operator of the total magnetic moment. Now the total magnetic moment, we said, is the sum of the elementary magnetic moments. And for the elementary magnetic moments, we have this formula below. This is proportional to the Pauli matrix. And also the magnetic field is pointing in the z direction, so we have only the Pauli z matrix appearing here. So the Hamiltonian, when you combine these assumptions, these formulas, you find that the Hamiltonian is given by Bohr magneton times the magnitude of the magnetic field times the sum over all ions going from 1 to n times the Pauli Z matrix referring to the ith ion. The Pauli matrix 1, 0, 0, minus 1, Pauli Z, pertaining to the ith ion. This is the Hamiltonian of our very simple model for a paramagnetic salt. As usual, we are facing now the task to construct the state, the macroscopic state of the system. And in order to do so, we should first make a list of the macroscopic data that are given to us about this paramagnet. What are we given? We're given the external field, B. This is in our structure that we discussed, in our general framework that we discussed. This is macroscopic data of type 1. That's an external field or a control parameter. Then we are given the total number of ions, N. This is given as a sharp constraint. Now we have a lattice and the number of, there are no ions that can escape or be added to the lattice. It's constant in time, it's fixed, and it's given as a sharp constraint. So this is, in our logic, macroscopic data of type 2. And it means the way we process that is that we work in the Hilbert space of n ions, in an n particle Hilbert space. And then finally, we are generally given the energy, the total energy of the paramagnetic salt. So the total internal energy, U, this is one possibility. We might also be given the total magnetic moment, M. But these two pieces of information, they are in fact equivalent, because the energy is given by minus external field times magnetic moment, so minus B times M. So if we know M and we know B, then we also know U. Or if we know B and we know U, then we also know M. Provide information about either of the two, and then you can calculate the other. So these are two equivalent pieces of information. Now this might be given either as a sharp constraint. Say if the system is isolated, no heat exchange, no energy exchange of any form, in particular no heat exchange with the outside world, then this might be given as a sharp constraint. Or if you allow exchange of heat, then the energy is not fixed. It has no sharp value, and then it may be given to you as an expectation value. So let's assume the latter case, and let's assume that it's given as an expectation value, and in this case we have type 3. This data is of type 3 in our logic. This is an overview of the macroscopic data that we are given. Next we have to construct the state, the density matrix, to describe the system. We have to construct the macrostate. Macrostate is, that's the density matrix. Which density matrix do we choose? The only expectation value that is given to us is the expectation value of energy. And we had discussed in our general framework that in this case we should use the Boltzmann-Gibbs state, the state that maximizes the entropy. So we use Boltzmann-Gibbs, and this has the form 1 over partition function times e to the minus beta h, where the partition function is the trace of e to the minus beta h. And now the Hamiltonian depends on the control parameter, depends on the external field B. Therefore, the partition function 2 depends on B. The partition function also depends on the beta, the inverse temperature that appears in the exponent. And we are working in the Hilbert space of n ions. So this is or n spins. Yeah, the magnetic moments correspond to spin 1/2. So we have n spin 1/2. So the Hamiltonian is an n spin Hamiltonian, and the trace is in the n spin Hilbert space. And therefore, the partition function also carries a dependence on n. So immediately with our general recipe, we know how to write down the macrostate, and we have a formula for the partition function as a function of its natural variables, and its natural variables in this case are b, beta, and n. We know from the Guggenheim square and all the relations that are encoded in the Guggenheim square that once you know the partition function or the log of the partition function, then from that you can basically calculate everything else. So in this example and also in all other examples that will follow, the main calculational task will be to calculate the partition function. Before we do that, I would like to talk about an interesting feature here that simplifies a lot the calculation of the partition function. And the fact is that we said that we neglect the interaction between the ions, between the spins, the elementary magnetic moments. So we have a composite system where the parts do not interact with each other, to a good approximation. Mathematically, this manifests itself in the fact that the Hamiltonian of the total system is simply the sum of Hamiltonians of the individual parts. So independence and lack of interaction between the parts means that the total Hamiltonian is simply the sum of the Hamiltonians of the individual parts. This is a slightly sloppy notation because you may wonder, well, the HI is a Hamiltonian, it's an operator that lives in the Hilbert space of the ith part, and how can I add up objects that live in different Hilbert spaces? Yeah? So, strictly speaking, you should write the total Hamiltonian is the Hamiltonian of the first part, tensor, unit operator, tensor, and so on, they are all unit operators, plus unit operator in the first Hilbert space, tensor Hamiltonian in the second, tensor unit, and so on. And then you add up over all the parts. So you're adding up objects that live in the same Hilbert space. This implies that when we exponentiate that, so we have e to the minus beta h, where h is now the total Hamiltonian, and hence this exponential is an operator in the composite Hilbert space. When we use the fact that the total Hamiltonian is just the sum of the individual Hamiltonians, then this means when we exponentiate that the exponential is the product, and more precisely the tensor product, over all parts, all constituents I, of the individual exponentials. So each factor in this tensor product is an operator in the Hilbert space of the ith part. This implies that the partition function of the total system, that's by definition the trace of e to the minus beta total Hamiltonian, this is the trace of this tensor product, but you showed on one of your problem sets that the trace of a tensor product is the product of the traces. So this is the same as the product of the traces of e to the minus beta hi, where now the traces here are taken in the individual Hilbert spaces of the individual parts. And this you can call the partition function of the ith part. So then you write this as the product of the partition functions of the individual parts. So in this sense you can say that the partition function factorizes. The partition, when you have a composite system composed of non-interacting parts, then the partition function of the entire system is simply the product of the individual partition functions. This holds generally. Now in our specific example, we have that the individual Hamiltonians of the individual spins that generate the magnetic moment, they all have the same form. They all Bohr magneton times Pauli matrix, all the same form. So, in fact, it's necessary to evaluate the partition function for a single spin only, because for all the other spins, it will be the same. It will look exactly the same. Yeah? So, rather than evaluating the partition function of the entire paramagnet, it's sufficient to evaluate the partition function of a single spin. Yeah? And let me call that partition function of a single spin Z1. And then, once we have that, the partition function of the entire system of the paramagnetic salt is simply this Z1 to the power n. Because it's the total partition function is the product of the individual partition functions, but they are all the same, so we just have Z1 to the power n. And this is an immense simplification of our calculation. Before we proceed to actually calculate the Z1, let me just mention to you a number of further consequences, which are quite general, of this factorization. A first consequence is when you look at the Boltzmann-Gibbs state of the total system, and it's 1 over the partition function of the total system times e to the minus beta total Hamiltonian. We just learned the partition function of the total system is the product of the individual partition functions. And we also know, that was our starting point, the total Hamiltonian is the sum of the individual Hamiltonians, and therefore the exponential e to the minus beta h is the tensor product of the individual e to the minus beta hi's. So using these two features, we can write the Boltzmann-Gibbs state as a tensor product over all the parts, and then 1 over the partition function of the individual part times e to the minus beta Hamiltonian of the individual part. But what's inside the bracket, this is nothing but the Boltzmann-Gibbs state of an individual part of the system. So this is the same as the product of Boltzmann-Gibbs states of the individual parts. So in particular, you learn that the Boltzmann-Gibbs state of the total system is a product state. It's a tensor product of the states of the individual subsystems. And we talked generally about correlations between systems. We said that whenever the density matrix of a composite system is the tensor product of the density matrices of its parts, then this means that there are no correlations between the parts. So this shows you immediately that this is a product state, and therefore there are no correlations between the parts. Another consequence is when you look at the log of the total partition function. Since the total partition function is the product of the individual partition functions, once you take the log, then you get, this is the sum of the logs of the individual partition functions. Next, let us look at the total energy. The total energy, how do we obtain the total energy from the log of the partition function? Think of the Guggenheim square. The log of the partition function has as its natural variable the inverse temperature beta. Or when you take a partial derivative of the log of the partition function with respect to beta, you obtain the associated expectation value with a minus sign, which is the internal energy. So U is given by minus partial with respect to beta of the log of the partition function. We just learned the log of the partition function is additive, so this is minus sum over I d over d beta log of the individual partition function. But you can say minus d over d beta log of the partition function of a part. That's the energy of that part. So this is the internal energy of the ith part of your system. So you find, which is also very intuitive, that the internal energy is additive. The energy of the total system is just the sum of the energies of the parts. What else can you say? You can look at the total entropy. The total entropy, that's K log total partition function plus K beta times U. Now again, we take that from our general formula. We use additivity of log z. So we have k sum of rho log zi plus k beta, and then we use the additivity of energy. That's simply the sum of the ui's. And therefore you have, at the end, you have the sum of all parts, and then you have k log zi plus k beta ui, which is just the entropy of that part. So it's the sum of the entropies of the individual parts. So also the entropy is additive. And this, by the way, is as it must be, because if the overall state of the total system is a product state, that's what we had found above, that the state of the total system is a product state, we know from our general properties of the quantum mechanical entropy that the entropy of a tensor product is the sum of the entropies. And that is, of course, consistent with what we just found, that the entropy of the total system is the sum of the entropies of the parts. So these are very general properties that are not true only for the specific example, but they are true generally, and we will use them again in the future. Now, at this point, and this will conclude today's lecture, let me calculate the partition function of the paramagnetic salt. We said that all that we need to do is to calculate the partition function of a single spin, Z1. This is equal to the trace of e to the minus beta times the Hamilton operator, the Hamiltonian, of a single magnetic moment. But we said that the Hamiltonian of a single spin, this is Bohr magneton times external magnetic field B times the Pauli Z matrix. The Pauli Z matrix, remember, is diagonal, it has entries +1 and -1. So, and it has eigenvalues +1 and -1. This means that the exponential has eigenvalues e to the minus beta Bohr magneton B and e to the plus beta Bohr magneton times B. And the trace is just the sum of the eigenvalues. So this is equal to e to the minus beta Bohr magneton B plus e to the plus beta Bohr magneton B. And this is equal to 2 times the hyperbolic cosine of beta Bohr magneton times B. This is the partition function of a single spin in your paramagnetic salt, in your lattice. And this implies that the partition function of the entire paramagnetic salt, this is just this individual partition function to the power n, and therefore this is equal to 2 times the hyperbolic cosine of beta mu b b to the power n. And as expected, this total partition function is a function of beta. It's a function of the external field B, and it's a function of the number of ions n. So all three variables that we expected to appear in the partition function do in fact appear in this formula here.